Oh, but
But it doesn't matter. We have the first speaker. So.
Lavinia can present on the
Yeah, just go for it. Why not?
Is it active? No, that's not working now.
No.
We're
It's okay. Yeah.
I think I have to change my Mac settings.
Oh,
It's
you're not
going
using the this one.
Yeah, wait a minute. I think I have to
You're
go
not
to
using the
settings
this one.
and then sound.
You're not using the this one.
Output, sound.
You're not using the Plantronics. Plantronics. Yes, it will. Yes. Okay. Can I start?
Yeah.
Okay.
You're in the
I'm gonna start. So again. Okay. Hi everyone. We're starting with science last day here in Oslo division. Thank you for coming. That's great. We're having lots of people here, and we're going to have first a presentation of our division was part of it, and then we're having a quiz about the stuff we're going to learn today. And the speakers are going to be three. Hmm? Okay, we're going to have three speakers, and we're starting with Emanuela Di Martino. That's here. Welcome. With Borav afterwards. He's here, and with Anya later. That I think she's not here yet, but she's supposed must be running late, but she's coming. And yeah, thank you so much. In between speeches, we're going to have a 10-minute break, so you can, grab beers then, or go to the restroom and take a break. And also, I have to mention thanks to House of Nerds, the place we're using today. It's very good. And okay, now it's time for Lavinia, the leader of our division. So.
Um, so first of all, what is Pint of Science? So Pint of Science is an international organization working on science communication. Science communication that we try to do in this way. So we try to gather people in places like this, in bars, in pubs, and offer, let's say, science in a kind of a funny and easy way, um, the way you can enjoy, where you can relax, you can chill and have a nice pint of beer. You can also listen to our speakers. And Pint of Science started actually in the UK in 2014, and then it spread quite quickly all over the world. So this is a quite accurate picture of Pint of Science 2019. A lot of countries, a lot of cities. The situation is updated in 2019 because there was the pandemic after that. So probably something more happened, but not a lot. And what the situation in Norway? In Norway, we have 5 cities, so that means 5: Oslo, Stavanger, Bergen, Trondheim, and Oslo. And the- what the Pint of Science does basically is organizing this event, this festival, every year. And this is happening right now in all the cities that are joining Pint of Science. So it's something happening in this current moment all over the world. And we're having, yes, 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 a round of applause. We're, is it working? Maybe. Yes, yes, maybe, yes. Um, so we're having a five festival right now in Norway. And you can follow us on social media. You can upload to the website, and if you have any question, you can write to Norway at pintofscience.no. And this is the team that's working in Oslo. One thing that I want to say that we are all volunteers here. So everything you see, you have seen in the days that you will see, was done by these people in our spare time. So it's something that we do, yes, for free as a volunteering activity. And so I'm very, very grateful to every single person that you see there, and most of them are also here. Nothing could have been done without the help of every single person. And of course, we couldn't be here without our speakers that are also giving their time and their knowledge for free, and we're very thankful for this. Is preparing this type of contributions, this type of presentations is kind of difficult and hard. Trying to explain your research in a different way. So we're very, very grateful for your efforts and for the time dedicated to preparing these presentations. Another big thanks goes to our sponsors because, again, we're doing everything as a volunteering activity, but everything has a cost. And so without our sponsors, we couldn't do basically nothing. And the Simula is supporting Pint of Science Norway in the beginning, let's say, of this journey in 2020. And Simula has supported Pint of Science Norway since the beginning. And also the Italian Institute of Culture is supporting Pint of Science, different editions and different events. And it's I think the third or fourth event that the institute is supporting. So thank you very much to our sponsors and supporting institutions. And we need your feedback. We would like to have your feedback, improve um, our work, try to do something better next year. So if you wanna tell us what you think about these nights, please do it. It's very important for us. And of course, we are always um, we're always happy to have new volunteers. There's always work to do. So if you're interested in science communication, if you want to do this, if you like this night, if you do this next year together with us, just join the team. And we missed the code. Oh, but you will see in a few seconds. So we have to have ready with Peter um, and Sean here is gonna handle the quiz, show you the code to actually to join. To restart the system.
Tell some jokes.
Yeah. Um, but I'm not very good at improvising. So
English.
no, we're almost ready. So I'm gonna leave you the mic and the floor.
Thank you. Let me mic up. Okay, I think 20 people are on. That should be enough time for everyone to have joined. One last. We're going ahead. I think you can still jump in once we started anyway. Okay, but you better be fast with your fingers because transferring quickly. So that's the other thing you need to know. Okay, let's get on with it then. First question. Answer fast to get more points. The name Bryozoa comes from Greek, but what does it mean? Colonial animals, funny animals, moss animals. This is the one you had a preview of, so I'm not giving anyone excuses for getting this wrong. Everyone has voted. Oh, wow! People were genuinely closing their eyes. Okay, well, there you go. The 13 people did it before I got the presentation working, and the answer was moss animals. Right, next question. Oh, yeah, we get to see the leaderboard then. Who are these clever people who either knew it or saw it? Great. JL leading the way. Question number 2. Has to get more points. Where does the Gulf Stream go from and to? From the Tasman Sea to the Sea of Japan? How good's your geography? Gulf of Mexico to the North Atlantic? Southern Atlantic to the Gulf of Guinea? Fastest fingers first. Hey, almost everyone knew that. 2 people, maybe these people in the corner who are giggling, I don't know. Okay, almost everyone got that right. Nice. Let's check how it's affecting the leaderboard then. Oh, sorry, JL. JL's already slipping down. Joanna's Santa is winning. Yay! Go Santa. Number 3, still all to play for. Oh, sorry, it didn't press the button. There we go. What's special about storing CO2 underground in Iceland? Iceland. CO2 quickly turns to stone. The space due to the volcanoes. The glaciers prevent it from escaping. Oh, people not sure about this. Everyone has voted. Oh, mixed answers. Only 6 people got that right. The CO2 quickly turns to stone. If it hasn't occurred to you yet, these are all questions that relate to the talks we're going to hear. So Don't feel bad if you didn't get it wrong, because we're all going to learn something tonight. Joanna's killing it. Joanna again at the top. Huh? That's true. But I didn't talk about Iceland. Yeah, there was a bit of stuff about CO2 in yesterday's talk, but it wasn't about Iceland. So, hey, how many species of Bryozoa currently live in the global ocean? Extinct. Are there more than 6,000? Are they very, very rare? Fastest fingers first. Hey, more than 6,000. There are bloody loads of them. Who knew? They're everywhere. Oh no, Joanna! Joanna, you've had a mare. Petro Boy. Okay, Petro Boy. Well done. Let's move on. Next question. In what year did the Spanish explorer Ponce de Leon, that's probably not how you pronounce it, note the strong current that's now known as the Gulf Stream? Way back in 1513, 1705, or 1879. What do we reckon? Oh, nice. Yeah, way back. We've known, or at least known about the Gulf Stream for 500 years. Here we go. Joanna is struggling now. Sorry, Santa. Goodbye. Next. Oh, come on. If anyone gets this wrong, you need to rethink it. Okay, what's the main reason why the climate is getting warmer? Is the Earth getting closer to the sun? Is the sky clearer because there's less pollution? Or is it the emissions of greenhouse gases? Oh my gosh. Okay, one person is trolling. That's definitely a troll. That's just a straight up troll. Petra Boy. Wow, okay. He's oh wait, no, it's not the fastest that time though. It's still in the lead. Still got a clear winning lead. All right, last few questions. When did Bryozoa first appear on Earth? 500 million years ago, way before dinosaurs and humans. Same time as the dinosaurs, same time as the humans. 16 people away. Most people know that Bryozoa go way back. Anyone knock Petra Boy off? Petra Boy! No, Petra Boy got that one wrong. He still got the top spot. Okay, there's definitely all to play for. The last question, and we can definitely knock Petra Boy off the top spot here. Come on. Why do scientists spray water droplets in the air off the Australian coast? Just cooling down the tourists, improving the fishing conditions, or making clouds that protect against heat waves. Hey, people thought, yeah, a couple of people thought that fishing conditions, but no, mostly people knew that isn't fine the engineering solution as well. Okay, so let's see, Petra Boy. Oh, Petra Boy took a bit longer to think about it. Oh, it's so tight. Oh, there we go. Hungry. Who's hungry? Is that you hungry? Hey, well done. Okay, we do have a prize. Where is that prize? Hungry, you've got a prize. Da, 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 da. Oh, I'm gonna pull my mic. I can't move any closer to you. I'm gonna pull the microphone off. There you go. Well done. Congratulations, Hungry. Okay, there you go. That's the end of the quiz. Back to our host. Yes, you can have fun. Do you want me to just give that to you?
Yeah, thank you. Okay, so that was fun, but now we're ready to start with scientific talks. And first we have Emanuela Libertino. She got her PhD in paleontology in 2014 from the Utrecht University as a Marie Curie. Yes, sir. She later got experience from the museum in Dublin, And then it was awarded a 4-year project here in Norway. And yes, now she's here, ready to tell us more about her research.
Okay.
Yes, you need this one.
Too many cables today.
Yes.
It works, yes.
Se ho acceso.
Sì, me l'ho acceso show. Hello everybody, thank you for being here tonight. My name is Emanuela Di Martino. I'm currently a researcher at the Natural History Museum here in Oslo. I am a paleontologist with a background in geology and an expertise in a group of aquatic invertebrates called bryozoans, or informally moss animals, in Norwegian moose deer, which are often obscure to the general public. And as a Natural History Museum, we have a mission that is to preserve past and present biodiversity. And I understand that can be very difficult when the organisms are not so well known, as it is often the case for bryozoans. Today, I will walk you through the fascinating world of bryozoans. We'll see together what they are and why they are important to be known. So first of all, what are bryozoans? Raise your hand if you have ever heard about bryozoans or moss animals before this event was advertised. Okay, that's not bad, I would say. So this is usually the image, and these are the specimens. You can pass them around, that I show to people when I want to start a conversation about bryozoans at public events. I usually ask, do you know what is this? Have you ever seen anything like this? And because this species is quite common along the North European coasts, like in Norway, it's quite easy that you find it stranded on the beach. So usually people say yes, they have seen it, and they think it's a seaweed. As soon as I say that actually it's not a plant, but it's an animal, a colonial animal, like the more popular corals, people are kind of surprised and keen to know more. I hope you are keen to know more as well. And because of their similarity with plants, actually bryozoans have puzzled natural scientists for centuries. The main questions being, what are they? Are they animals? Are they plants? Are they something in between? Are they the common ancestors between animal and plant? And even the name bryozoans that we have just seen that derives from the ancient Greek, and it means, of course, most animals, reflects this similarity between bryozoans and members of the plant kingdom. On your left side, you see some encrusting colonies of bryozoans. On the right side, some common lichens. And you can see that the similarity is uncanny. Bryozoans are invertebrates, as there are many others living in the land or in the sea. They are invertebrates as insects, as corals, as crustaceans, sea worms, mollusks, sea urchins, and sponges, and so on. But they are colonial invertebrates, so they form colonies that are composed of variable numbers of modules of individuals. In the pictures on your right, you see a scanning electron microscope. So if you look with the microscope at those specimens that you've just seen, you will see those individuals that are box-shaped and all connected together because they need to share resources. They are all genetically identical, but they can have different shapes and different functions within the colony. All those functions are necessary to keep the colony alive. There will be modules devoted to feeding the colonies, some others in charge of reproduction, some others that will clean the colony, some others that will defend the colony against predators.
I didn't check the presentation before, so you cannot see the text, but doesn't matter. So they are an important component of present and past biodiversity. There are more than 60,000 species living in the oceans today, but there are more than 15,000 species that have been described from the fossil record. And as you can see, they can grow in a huge variety of colony forms. We have seen already frustra that is flexible, erect, flat, but they can grow as erect cylindrical branches. You can see here and you can pass around. They can be more foliaceous. You can have this and pass around. That is the foliaceous one. They can be bushy and soft like this. They can be, they can grow as encrusting sheets on rocks or shells like these ones. They can be very nice like these ones and form lace-like three-dimensional structures. I can prove. This depends, of course, on the nature of the species, but also the characters of the environment, like if the environment is low or high energy, if there are huge substrate available or only small, and whatever. As I said, they are all aquatic. They are mainly marine, but we can really find bryozoans in any kind of water environment. We can find them in freshwater and brackish environments, so rivers, lakes, lagoons, and of course in the sea. They can be at all depths, from the intertidal to the very deep waters, at all latitudes, from the equator to the poles, in the northern and in the southern hemisphere, everywhere. And of course, depending on the type of environment they colonize, the groups of bryozoans we see there are different. In the freshwater and brackish environment, we usually have bryozoans that are soft-bodied or with a weak mineralized exoskeleton, external skeleton. In the sea, we find only mineralized bryozoans. They form an external skeleton that is made of calcium carbonate. There is another thing that changes depending on the environment, and it's the diversity of the fauna. In the freshwater and brackish environment, the diversity is usually low. We have a total of 20-25 species described from those environments. In the sea, the diversity peaks between 0 to 100 meter depth in the shelf environment, and then the diversity decreases at increasing depth. They are suspension feeders, which means that they eat particles that are suspended in the water column. And to catch them, they use a feeding organ that is called lophophore, and is this crown of tentacle you just see. Yeah, I can use the with these tentacles, they can make microcurrents, so they can make the water move and change just what they have on top of them. They can get the particles of food, usually phytoplankton like microalgae, or they can spit out other solid particles that are not food like sediment grains. And they are usually sessile and benthic, meaning that they need a substrate to grow their colony. So they are fixed to the substrate, which usually lie down on the seafloor. This substrate can be of any kind. They can be long-lived hard substrate, like rocks, like in this case, or hard substrates that are of biotic origin, like shells. We have seen some of the shells encrusted. And in this case, when bryozoans grow as encrusting sheets on long-lived substrates, we can actually observe competition for space. So in this image here, you see one of those shells that you have been passed around that is richly encrusted by bryozoan. On the other side, you have a scanning electron microscope image of the area that is outlined in green. Here you can probably distinguish the different colonies, but also the different species. And in this case, you see that some species are able to win this combat for space, like in this case here. You see this species here is overgrowing this one, or this on top here is overgrowing this. Some other species won't be able to do so. So what they do, or they are overgrown, like in these two examples here, or they just stop growing, like these two over here. So this is also kept in the fossil record because they fossilized, and that allow us paleontologists to study ecological interaction in the past, and also to study the behavior of different species through time. As I said, they can encrust any kind of substrate, even ephemeral substrates that just last for a season, like algae, for example, or seagrass leaves or stalks. In this case, of course, the duration of the colony is strictly linked to the duration of the substrate, which is usually seasonal. But if you remember, I said that they are usually sessile. There is a group of bryozoans, like those two guys that you see here that have these nice Chinese shaped colonies that are able to move freely on the seafloor. How do they do that? They use some specialized modules called vibracula that can develop these filaments here that are called setae, and they use this to move on the seafloor. This group of bryozoans are adapted to soft sea bottoms, seafloors that are made of loose particles like sand or gravel, and to high sedimentation rate. So there is a lot of sediment coming down to the water and depositing on the substrate. So if they would be sessile like the others we have seen, they would have been just buried and die. But these guys can unbury themselves using those data. And as I said, they have a calcium carbonate skeleton that is made either of calcite or aragonite. And this allows us paleontologists to find hundreds and thousands of colonies in rocks and sediment deposits. And this is good to make significant paleoecological and environmental reconstruction, but also for microevolutionary study through time. Also because bryozoans have a long and successful evolutionary history. As we have already seen, the first bryozoan body fossil was found in Cambrian rocks that are dated about 520 million years ago. So they started long before dinosaurs and even longer than humans. And compared to those other much more popular group of fossils like dinosaurs, they are still alive today and very successful, very diverse. By now we should have an idea of what bryozoans are. But why are they important to be known? I will show you some examples of what bryozoans can tell us and why they are important. So first of all, they are important ecological players. They are part of the sea, of the food web. As we said, they are consumers, of course, they eat phytoplankton, as I already mentioned, but they are also prey. And here you can see different groups of other organisms grazing on bryozoan colonies. Who likes the bryozoan meat? Slugs, for example, but also some gastropods, sea snails, some small crustaceans like amphipods, and especially spiders, pycnogonids. Bryozoans are also an important habitat constructors, and here you have some examples of two seafloors that are mainly made of bryozoan colonies. Being habitat constructors means that they can shelter an associated community that is very diverse. They offer space to live for other bryozoan species, but also mollusks, cnidarians, arthropods, all kinds of invertebrates that live in the sea that you can think of. And they are also ground nursery for some juvenile fish species. But being an habitat constructor means that they are also potentially under threat due to global climate change and ocean acidification. And actually, bryozoans are one of the best model systems to study the effects of future ocean acidification because of the calcium carbonate skeleton. And here I want to show you some studies, an example of ocean acidification study that has been conducted in Italy in the Tyrrhenian Sea off the coast of the Ischia Island, because there is a natural acidified laboratory because of volcanic carbon dioxide vents. So the scientists have chosen 3 sites. This was before that one. S1, S2, S3 that are distant from the vents. S3 is the closest to the vent. S1 is the more distant. In this case, S1 doesn't feel the effect of the production of the so the pH is normal. And it's lower in S2 and the lowest in S3. And they use 2 species of bryozoans, Myriopora truncata, which is also known as false coral because it's very similar to the red coral Corallium rubrum, and the Calpensia nobilis. They use these 2 species because they are habitat constructors, very common in the Mediterranean. So this is how they look like at normal pH of 8.1 at type 1. Okay, doesn't matter if they appear all together. So this is how they appear at S2. So you can see the effect of the distribution already in Myriopora, because if you compare the pictures, you see that here the pores are more numerous and larger. You don't see much difference in the modules of Calpensia, although some of them are incomplete. And if you we go to site 3, where the pH is down to 7.3, you see the vulnerability of Myriopora. The skeleton is almost gone, but you see something different in Calpensia. Calpensia, when the pH goes down, start growing slower, so the colonies will be smaller, but it will make modules that are more robust. The skeleton is more robust. You can see the difference here. So what does this tell us? It tells us that we should be concerned about species like, I forgot to tell why they behave differently. Because of a different mineralogical composition. While Myriopora is made of high magnesium calcite, Calpensia is made of calcite and aragonite together, and the calcite is of the low magnesium type. So what they tell us is that species of bryozoans, but also other organisms with skeletons made of high magnesium calcite, will be very vulnerable in an acidified oceans, and we risk to lose them completely, lose them and all the habitats they provide. In the case of Calpensia, it gives us some hope because it means that some species can still cope with acidified waters, so they can somehow adapt to the new condition, although they will grow smaller and they won't anymore be real habitat constructors. Another important thing about bryozoans is that they are a source of bioactive compounds with a potential benefit for human health. So they provide metabolites that are being tested for the treatment of some human diseases, especially those related to viral infections or parasitic diseases or brain diseases. And this is a long list of species that have been already tested. There are 26 species tested for a total of 230 compounds. So only 26 species. There are 6,000 living out there, you see that there is a potential for novel discoveries, and we hope they work out. But I want to show you one species that is Securifrustra securifrons, because this species is very common off the coast of Norway. It's very common in Norwegian waters. And the metabolites that have been isolated from Securifrustra securifrons are being tested for the treatment of some human cancers. So fingers crossed there. And the last thing I want to show you is why we should know the regional fauna in each country, and why we should also monitor bryozoans, because they are very good fowlers, so they can grow on any kind of substrate, even anthropic substrate like metal or plastic. And they can be a challenge for the maintenance of maritime infrastructures, like those for renewable energy, for example, in which Norway invests a lot. And this is just a small example of what they are able to do. These were clean crayfish cages that have been in the sea for 6 months, completely clean when they were put down. And this is how they came out. So they are fully encrusted by bryozoans. They looked beautiful. They were really nice, even for us that study them, but I can tell you that the fisherman was not so happy to see this. And because they are able to foul anything, they also foul the hulls of shipping vessels. So they can be able to travel for very long distances. And those species that do that are invasive species, species with a high resilience. So they can live everywhere, even if the water is very polluted. And they are usually a threat for the endemic fauna. So they can damage the endemic fauna. And that's why we should keep an eye on them, also to monitor the changes in regional fauna. And I think this is all from me. I hope you have learned something new, something nice. And thank you so much for listening. If you have questions, of course, happy to reply.
Presentations was very. I think. Can you hear me? Oh, for this room, yes. No, I just want. Is this working? Yes. I was just wondering if I'm not sure I understood what makes them an animal or not a plant.
First of all, that they are not autotroph, so they can just use the light of the sun to produce nutrients using water like plants. They have to catch their food. That's one of the main differences. Okay. And also, if you look at them when they are alive, in each of these box, you will find an animal that is called polypide, that is like the polyps of corals. If I can go back. This one. So you see, this is the animal itself that goes out from those box-shaped mineralized skeleton.
Any more questions? Okay.
So this was supposed to go without me clicking the button.
Use the arrows if you want to.
So I think that you have already partially answered my question while you were presenting. Thing is that because they are so subjective to the acidification of the seawater, I was wondering how they can, like, how they could survive to the 5 big extinction, because some of them have been caused by, big volcanic eruptions. So I just imagine a lot of acidification in the water. So I think now, because of your presentation, that survived some species of them, in particular those with low magnesium in the
Calcite,
Yeah.
yes. And also you have to think that we have had already 6 big extinction events, and they survived that. Yeah. So they are at least a hope in this changing world comes from Places.
So very resilient. Yeah. So any questions? Oh, there.
Just one question. During your presentation, you mentioned that they are colonies.
Yes.
and that they can have different roles in the colony. But do they have differentiation in their morphology? Or
Yes,
do it
they
at the
do.
physiology?
They are polymorphic. Actually, I didn't have the time to show the different structure. So if you use the last. So this box will be the feeding modules that when it's alive, this is just the skeleton will feed the colony. Then this structure here that is rounded, that will be the chamber. You see that the zoids, the modules that just feed have different morphologies from those that are incubating because they have this morphology, this ball on top of them. Then these ones that you see, they are like triangular with a sort of beak and a mandible. Those are the zoids, the modules that are used for defense. They have these mandibles that should scare the predator away when they approach. So in the colony, you can distinguish who was doing what. You can also quantify how the colony was spending its resources because depending on the environment, if they at the beginning, if they need to just grow, they will just produce feeding modules. Then at some point, when they are capable of maintaining the colony, so they will spend the resources for other things like the avicularia, they are called against the predators, or to start reproduce. Of course, they reproduce sexually within the colony, so they just bud another module and they reproduce sexually when they make new colonies.
Okay. All these forms will be individual.
Yes.
Yeah, the same.
So yeah, all the zoids are genetically identical. Yeah.
Thank you.
Yeah, here you cannot really see that, but on the lateral walls there are holes, there are pores, and then they have a funicular system that brings the nutrients from the feeding zoids to those like Pularia. They cannot feed, so to survive, use those mandibles. They need energy from someone else that is able to feed. So they will have connection through the walls.
Any more questions? No? And thank you.
Thank you so much again.
It's Bryoza. Oh, sorry. Okay. And now we're going to hear about the goal. Of course, of course. So, okay, another group, 10 minutes. Yeah, grab a bit. Stretch the legs.
Nice job. Thank you. The presentation was a bit disorganized. Grazie.
those that are buying stuff, hurry up. Actually, we're just going to start now. So we saw the effects of climate change in Moscow, and now we're going to hear about the Gulf Stream collapse from he's going to talk about climate models and how they differ from actual data, and we're going to learn a lot about it. So, Adam Postgren, please. Thank you. Yes. Okay. When you're ready. Second.
Thank you. So Gulf Stream, something discovered in 1513. 500 years history, 200 of them in controversy. So Gulf Stream carries 100 times the water that all the rivers on this planet combined, and that current is shutting right now as we are in this hall. That is something big. Now picture this: you're sitting in a cafe, talking among your friends, and secretly scrolling through TikTok as well, watching some videos, and this news clip pops up in your stream. That is for warning signs of Gulf Stream collapse, and it's from 2021. You must, all of you have seen this particular news clip. Now, what immediately follows this is there is a barrage of tornadoes that rip through the city on the west coast of United States. And these are the visuals that you can see in the United States. In Delhi, we are getting snowfall. So people in Delhi are happy they're getting snow for the first time. Since the Gulf Stream has shut down, all the water Gulf Stream was transporting from the equatorial region to the west of Europe. That water is now coming back, pushing into the east coast of North America. And there is tsunami. This is what we are getting into. These are the visuals that were playing in loop for more than 3 months, 2 years ago, when this first report came out, and it became a matter of public discussion for a very long time. These are the visuals of the day after tomorrow. But the typical American thing, the world was confined to just United States. They didn't talk much about what will happen to Western Europe. So I took the responsibility to tell you what will happen to Western Europe. So here you can see in summertime, the summers will be cooler by about 6 degrees on average when the Gulf Stream collapse is complete. And the winters will be colder by up to 12 degrees in the northern Norway. Things just don't end here. When it comes to the precipitation or rain or snow, they're both going to reduce. Lesser rain in summer, lesser snow in winter. The wind strength is going to increase, which means Western Europe will have much stronger and much more frequent storms because of the collapsed Gulf Stream. That heat engine that was transporting all the excess heat from the equator is no longer transporting to the higher latitudes. But one good news, you can ski for 10 months or more every year. So there is some fight in that as well. But these were results from 2015 publication. Climate models have evolved a lot in the last 8 years. So there was a publication this year, actually in March, that kind of said the same thing, that winds are getting stronger. There will be stronger storms hitting the west of Europe, and things do not look right for us. So what is happening? And this is not the first time this is happening, actually. It happened before, 12,000 years ago, when there was sudden crash. The temperatures, what you see are the Greenland ice sheet temperatures. And after 1400 years ago, something happened and temperature crashed down by 15 degrees. This is what we use as proxy to call younger dryas period. And this cooling lasted for about 1,100 years. I'll tell you the cooling that will happen now because of Gulf Stream collapse, at least for Europe. That impact will be visible even 200 years from now. That's how long it will take for Europe to recover from what Gulf Stream will do. And these are not just individual applications. IPCC report, a conglomerate of thousands of And they do also agree with that. Take this as a strength of Gulfstream, that Gulf, no matter what you do in any of the emission scenario from future that they keep growing, the Gulfstream is going to weaken, and you cannot stop that, no matter what you do from this point on. So the future is imminent. This is what we are getting into. Pack your bags, leave the planet. This is, I'm sorry, for sure. Wait. This is from the movie. Life is a bit more different. Life is not as simple. It's not a movie. There are much more complicated processes that are involved in establishing what is happening. The Gulf Stream itself is, as you already answered correctly, it's something which originates from Gulf of Mexico and hugs the east coast of United States and goes northward. That is it. That is Gulf Stream. It transports warmer waters from the equatorial region to the poles. Here you can see Gulf Stream in action on a monthly scale. It's pretty fast, 6 miles per hour. And you see the red color means warmer temperatures, blue color means colder temperatures. And you can see the seasonality as well. Here you see time changing. Winter, it's much colder there. In summer, it all mixes. It moves further up north. This is what Gulf Stream is, but Gulf Stream is just a part of a bigger system within North Atlantic. Now, this is bigger, which is this particular kind of conveyor belt system is very familiar to you because you have seen this in textbooks. The most horrible thing textbooks ended up doing, because this is absolutely wrong. And this is exactly the origin of the misconception we have what Gulf Stream will look like, what changes we will see into Gulf Stream because of all the climate change things. The younger dryas period, often it is said that a lot of fresh water from the Greenland and also from the north of North America that gushed into the subpolar region, and that led to the cold temperatures because Gulf Stream shut down 10,000 years ago as well. And same thing is happening now. That's a belief. But when we zoom in into North Atlantic region, things are slightly complicated there. There you see Gulf Stream bringing in the water from the equatorial region, and then Gulf Stream bifurcates. One branch goes southwards, not shown here. This is what Norway calls Gulf Stream. It is Norwegian coastal current, not Gulf Stream. And another branch goes in towards Greenland. This circulation is happening, and then there's deep water formation that happens in Nordic seas and partly in Labrador Sea. And this completes, Gulf Stream is just a branch of many other complicated currents that dictate the terms of ocean circulation. So just looking at Gulf Stream is meaningless to some degree. But just for simplicity, in media there has been a narrative that Gulf Stream is AMOC, AMOC is Gulf Stream, AMOC is Atlantic Meridional Overturning Circulation, a mouthful, but we call that fondly AMOC, which is much bigger, much more complicated than just looking at Gulf Stream. In AMOC studies, what we generally look for is how much water is being transported from equatorial region into polar region in the top 1,000 meters. That's how we define how much AMOC, how strong AMOC is. When we go a step further, Gulf Stream shutdown. If you Google that, you get 8 million immediately. So this is something people are talking about now more than ever. And thanks to some of the media job that was done we saw earlier, which messed up your coffee. And now when I just look at the Gulf Stream, this is a Bing search result. I am taken to this particular paper. I didn't search for Gulf Stream collapse. Bing automatically takes me. But what it says, let's look at it. It says Gulf Stream system is weakening. Why it is weakening? It says the slowdown of Gulf Stream system is unprecedented in past millennium. Gulf Stream is weakest in 1600 years right now. The Gulf Stream system is weakening because of us. I would partly agree to that if that is happening. The speed of Gulf Stream conveyor belt has declined 15% since the middle of 20th century. And these are not just random statements. They are paper that are published in Nature that show the same thing. There's one thing which is pretty consistent. All of them are from Nature. All of them are published by one institution, Potsdam Institute. I will name them. And this is the last one which made all the buzz in 2021, where this was the talk of the town for more than 3 months, that now we have evidences and observation that AMOC is weakening. Now the target is not Gulf Stream anymore. The target is the entire system of AMOC. So that has to be taken care of. And all of these papers that we just saw, they are based primarily on this one paper published in 1961 that largely considers ocean as two compartments. If you mess with one of them, the entire circulation will switch into a different state, to put it simply. Now, you know how complicated the ocean is. To imagine the entire system in one of the two boxes, it's impossible. Even if you have more than 5 boxes, it's not possible because there is a lot of regional variations in the way ocean changes and what time it changes and how the winds and other currents are changing. So what is really going on? So this wonderful publication that made absolute no news, complete silence, that did the data analysis from the observation. And what did they find? There are no changes at any latitude that we see at the moment in the last 30 years. The major contributor to changes in AMOC are the subpolar North Atlantic and dominantly east Nordic Sea region. So what is going on? From one point, we are getting all these messages that AMOC is going to collapse, Gulf Stream is going to collapse. Is everything normal? Answer is yes, Gulf Stream is not weakening. AMOC is stable. We do not have any conclusive evidence at the moment that it is weakening or not. And honestly, I don't know what will happen in future either. But this is the Arctic basin. Some of you might have seen it. And what you see in white flowing are the ocean currents. Now imagine putting that as one box. Moving on, so there in the Arctic Ocean, we see counterclockwise circulation. Although you do see current flowing here, but when you see from the satellite, all you see is sea ice. So this circulation is happening under the sea ice. There's something interesting is going on in the Arctic as we speak right now. In this region, which we call Beaufort Gyre, we do see a lot of freshwater pooling in. Now, Younger Dryas theory says when all the freshwater from this region pools into subpolar North Atlantic, which is essentially this area where deep water formation happens, it shut down deep water formation. So the water in the surface won't sink into the deeper layers and AMOC will shut down. And this paper, which is from observation, suggests there is a lot of fresh water which is being pooled in Beaufort Gyre now, which is waiting to be released in the subpolar North Atlantic. Now you will see I'm giving two completely different statements where at one point I'm saying there's no change happening in AMOC, but at the same time I'm showing you there is this Beaufort Gyre which is waiting to gush all the fresh water. And it's not less, it's 22,000 cubic kilometers of fresh water that is pooled in there. And at some point it will be gushed into the subpolar basin. How subpolar gyre behaves to the freshwater inflow is largely dependent on the computer model. And models at the moment, they are very sensitive to how much fresh water you put in. So to put simply, it does not matter how much you fresh water put in, but how fast you put all that fresh water in the subpolar basin. That matters for models. Everything is just to models because we don't know for sure how that happens in reality because our observations they are very limited. But what is the future? What's going to happen in the next 5 years? Let's not talk about next 50 or 100 years the way governments do. Let's talk what's going to come in next 5 years. So I'm answerable to you in just 5 years. Thankfully, WMO published on 17th of May a report that talks about what will happen in the next 5 years for Western Europe. Well, when we talk of global terms, the report says we with 66% confidence that we are breaching Paris Agreement 1.5 degrees at least once in the next 5 years. And these are annual means. So at least one of the next 5 years is going to breach 1.5 degrees. Forget about 2050 promises or 2030 promises. We are seeing it in the next 5 years. But what about Western Europe? Before we go there, there's something interesting that report says as well. is weakening next 5 years. That's what the report says based on the computer models. I'll come back to this later in a moment. But let's first look at what are we going to expect in next 5 years. So temperature, we saw cooling in the previous study, but what is going to happen in reality, we are going to see warmer temperatures in summer by at least 1 degree on an average. The precipitation is actually going to increase. So the summer will be warmer, it will be rainier, it will be slightly more stormier because of all the evening rain, because of thunderstorms that you see. When it comes to winter, winter will be warmer further by up to 3 degrees. So glaciers in Norway and everywhere else are under threat. The precipitation in winter as well is going to increase. But in winter, what matters how much rain you get and how much snow you get. The consensus is less snow and more rainfall will become a new normal for most of the higher latitude, and where we are. So smaller ski season, not 10 months. And coming back to AMOC, is AMOC actually weakening? And this plot that you see on the right kind of gives the answer. The confidence is very, very low on what we are projecting about AMOC, and there is a reason for that. All we know about AMOC is through computer models, but this is how much we know. This is the real observation that we have about AMOC in the last 50 or 60 odd years. So using just this much sample to make conclusions that AMOC is weakening or strengthening, or the world is going to end, or we are going to have these tsunamis of Atlantic water slamming the east coast of the United States, or we getting into the ice age, the visuals that we saw 2 years ago, it's a bit of a stretch, in my opinion. And next time when you hear someone talking about a Gulf Stream collapse or how the climate is going to change, it is good to consider, but there are far more important things that are happening with the climate. The greenhouse gas emissions, the kind of impact they have, compared to that, the impact of AMOC is negligible. I don't think we should even think a lot about it because oceans, I mean, all the heat that is in the atmosphere, the first 10 meters of ocean has more heat than that. This is a system we are talking about. It will take thousands of years for ocean to respond. Oceans respond very slowly to all the changes. So this message will continue. The debate, 200-year-long debate about Gulf Stream is not ended. It is still going on. Many of these papers, they are still contested by the day. There's still a lot of conversation going on. What is happening to Gulf Stream? But if there's one takeaway message for you today from this talk, I don't want to let you go without any final takeaway message. Let me show you instead of telling you. Whenever someone says Gulf Stream is collapsing, take it with a grain of salt. A big one. Thank you. Questions? Yeah.
So why is there so little data on what's actually happening to the Gulf Stream? How do we? Oh yeah.
Oh.
Is this enough microphones? I'm good now. Okay. I just wanted to ask why is there so little data? How do we currently monitor what's happening with the Gulf Stream? Do we send like a little message in a bottle into the sea and then try to like track it, or by satellites, or how does that work?
Good question. So there are a lot of ways we monitor. Primary way is satellites, but satellites just show you what's happening on the surface. So in order to go into deeper sections, we do have these arrays at various latitudes in the Atlantic. And on the right side, you see what's happening at each of them. In blue, you see what's going on in 1990, 1999. These are 10-year cycles. In green is what we are seeing now, 2010 to 2019. And in red, what happened in between those two periods. So the way we know what's happening in the deeper layers is we send buoys in there, and they once every 10 days they give you the profile. But there is only enough area in the ocean that you can cover. And this project started just 20 years ago. I said ocean takes thousands of years to respond, and we have the data sample that is less than 30 years. So when you are picking a 30-year slice and making estimate for 1,000 years with that confidence, using a model that is, is very biased towards how it reacts to when you put in fresh water, there, that's where things start to slip a bit. And as far as Gulf Stream is concerned, in your quiz, you said 1513 was the first time Gulf Stream was spotted. But for a very long time, 250 years, even after that, we continue to believe Gulf Stream is something which is just on the surface. Until one of the Reverend Stephen Hales asked one of the captains of British Navy who used to deal in slaves. In that slave ship, he was asked to take the water sample and measure the temperature in the deeper layers. So on one of his cruises, he used a bucket to do that. He put the bucket down into deeper the water, put it back, take the temperature, and he kept doing that until 3,900 feet. When he got beyond that, temperature won't reduce further. And he wrote a letter back to Stephen Hale saying that I don't know how much of use this information is for you, but the temperature kept reducing until 3,900 feet, and after that, it didn't reduce further. But it did help keep our wines cold and our water cold. So 250 years it took for us to understand that water beneath the surface is actually cold. 1971, 1751, sorry. And the first actual observation of Gulf Stream, they date back to just late 90s. So there's a huge gap, and we are dependent on the proxies, paleontologists, to give us some data. But again, since the science itself is not settled, the future of Gulf Stream is not settled.
Any other questions? Oh, yeah.
It's a sort of follow-up from Sean's question. She asked how you collect the data. What kind of data you need for your model, like water temperature, water masses? I don't know.
So generally we go with CTD, data collection. C means conductivity, T stands for temperature, D is for density. Conductivity means how much salt is in there. So in ocean currents, movements, the amount of salt that is there in the water and the temperature and how much it is at what depth, that is very important. But how this, when I said this deep water formation, now this is very complicated process. There, this kind of data set is not enough. There you need velocities as well in all the three directions and a very high frequency. So you can't have these data available all the time. So you have to set up experiments and set cruises specifically for a period of time to collect this data to understand how water from the surface is going, how much water is going in deeper layers. But for the models, we just given the salinity and the temperature profiles for the entire ocean. And also one thing we should keep in mind that so far, with confidence, we can say we know a little bit about the top 2,000 meters. What is below 2,000 meters, ocean is about 5,000, 6,000 meters. That again is a zone where we have very little information even now. So there's a lot of ground to cover before making claims.
Any other questions? No? Then thank you very much,
Thank you.
Goran. We're going to have a 10-minute break again. I'm going to talk about the effect on moss animals. Now, we saw the observations and climate models on the Gulf Stream and the ocean. Yeah. So take a pause, relax, and we'll come back in 10 minutes. We're ready to start with Anja Røyne. She's a physicist. She knows a lot, knows a lot about a lot of things. Interdisciplinary what is it? Background, which includes solar energy, rock weathering, nanoscale, surface science, technology, and economics. And she's published a few books, so she knows a lot about her field. Hopefully, we will learn a lot about it. So, and a post for it. And thank you so much.
Thank you. Is this on? Okay. Yeah. Okay. Hello. It's very nice to be here. You know, it's very dark and it's very nice and sunny outside. It's it's nice to see that you chose to be here. So, yeah. But is this not working?
That's for the online. And then this is for the one in the room.
Oh, I see. Okay. Yeah, that sounds better. Yes. So, in the talk before, I guess you talked a little bit about the climate and how things might be changing. What I want to talk about now is how we might do something about it. So, I call it engineering our way out of climate change. So, is that something we can do, or is it something we might want to do? So, I'm going to talk a bit about something close to home. This is a picture from someplace in Oslo where interesting things hopefully will be happening in the near future related to climate. And I'm also going to talk about clouds. But before I do that, I probably don't have to say that much about this because this is like a snapshot of climate. And yeah. Yeah.
Just go on.
All right. So there are bottom line. CO2 levels are going up very fast, up to a place where they haven't been for millions of years. So if we don't want to head into completely unknown territory, climate-wise, the time is now to make sure CO2 levels don't become too high. And how do we solve it? I think that's where we'll head. I think there's 4 things to think about. And the top 2 are the most important. This is an important part. So what do we need to do? We have to reduce emissions. That's like goal number 1. I just want to make that clear before I jump on to the next points. So emissions have to be reduced to avoid further warming. And then we also see that climate is changing right now. It has changed quite a lot, and it's going to keep changing. So that means that adaptation, which means that you just we change what we do, so that we will have as least bad consequences as possible from the changes that are coming. That's also important. That's 20 years ago, that might have seemed like a wrong priority, but now it's really necessary in addition to reducing emissions. But then what I want to talk about now is things that are a bit more science fiction, or they were, but now they're less science fiction, is that if we have put too much greenhouse gases into the atmosphere, then we might want to use some technology to take some greenhouse gases out of the atmosphere so that the warming doesn't get too much. And if that's not enough, maybe we can just put some shade on the earth, like put an umbrella up to avoid getting too hot while we clean things up. So those are the 2 things I'm going to talk about. Here's global emissions. So I think I need to point to this since I'm standing here. These are yearly emissions of CO2, and this is from year 2000. So this is in gigatons. It's very big numbers. emissions have been going up. Less the increase is kind of less fast than it was, but it hasn't really started to go down. It went down a little bit in COVID. It unfortunately went back up. And then these are projections of what emissions might do into the future. And they are color coded because they're based on different scenarios, and they end up with different warming levels. So this goes to the end of the century. If we have high emissions like today, what we end up with is unacceptably high levels of warming. And then we have the scenarios that take us within the Paris Agreement goals, which is that we want to reduce warming to 1.5 degrees Celsius, or at least 2 degrees Celsius. And what's interesting about these scenarios is not just that they have to start going down very fast. So today they have to start going down and go down very fast. But also that this graph is not zero at the bottom. It's zero here. So at some point around the middle of this century, which is not very far off actually, then emissions need to go to zero. So what does that mean? We have CO2 emissions every time you burn some fossil fuels. That's like positive emissions. The negative emissions below zero, means that you take the CO2 from the air and you collect it and make sure it doesn't go out again. And that's something we're not really used to thinking about. But if you see some of these scenarios, they end up at some 15 gigatons maybe of negative CO2 emissions, which is like substantial compared to the total emissions today. So it's really quite a lot that we're supposed to do. So how can we do that? How do we get CO2 from the air and somewhere else so that it doesn't contribute to warming? Well, it's possible to just do it with machines. If you have a submarine or if you have a spacecraft and people breathe in oxygen and then they breathe out CO2, then you get a lot of CO2 in the air and you have to take it out. So then there's machines with filters that suck up the CO2. And it's possible to do this also with atmospheric air. You just build a machine that has some kind of chemical filters in it, and you blow through the air, and in goes the air with a little bit of CO2, and out goes air with a lot less CO2, and then you collect the CO2. And here's what that might look like. So this is in Iceland, where they have plenty of clean energy because they are situated on more or less volcanoes. They have a lot of heat in the underground, and they also have a lot of water, so it's kind of easy for them to do this type of technology. So in this parking lot-sized installation, they have all these boxes with fans that suck CO2 in, and then they get the CO2, go into pipes, and then it goes further into these wells where it's pumped underground. So this installation here are some people for scale. So this is not huge. It captures 4,000 tons of CO2 each year. That's equivalent to something like 570 people in Norway. So it's not that big. It's doing something. I don't know. You can decide for yourself if that's a lot or a little. And then when this CO2 is pumped into the ground, it's mixed with water so that it becomes like a very acidic. And when it reaches the basalt, the volcanic rock underneath Iceland, then it dissolves some of the rock because it's so acidic. And then new minerals are formed that contain carbon. So that means that the carbon, the CO2 from the air, actually turns into rock. And it's going to stay there basically forever. So this is really a way to clean up the atmosphere and then just have the CO2 be gone. So that's possible. And they're actually now building a new project, which is even bigger. And if we want to use these things to do all of that CO2 removal from the atmosphere, we need 500,000 of these. So that's the scale. I don't know if you think it's a lot or a little. It's not that big, but 500,000 is a quite big number. Now that's using machines like this is not the only way to get CO2 out of the air, because plants do it all the time. Photosynthesis is taking CO2 from the air and turning it into something else. So it's turning it into biomass. So if you plant a tree, then you remove CO2 from the air. That's quite nice. But there's also a limit to how many trees you can plant, because we also need space for other things. And then the tricky thing is also that when the climate is warming, you have a lot bigger chance of damage to forests and forest fires and these things. So then it didn't really help that you planted all these trees. If they're just going to burn anyway, then the CO2 goes back in the air. So this can't really be the only solution. An alternative can be that you plant trees or something else that grows fast, you chop it down, you take it to a power station where you burn it instead of burning coal. Then you get heat and electricity, and if you don't let the CO2 go back into the air, but you capture it and you put it underground, then you have like a suction mechanism. The CO2 goes from the air and then into the ground and stays there. So that kind of gives us energy and it cleans the atmosphere at the same time. Unfortunately, if we wanted to do all of that CO2 cleaning that was shown in the first figure, using this method, it might require something like 2 times the size of India of growing plants. So it's not like the only solution. But this is going to happen, hopefully, if they find the money again on a small scale at the Klemetsrud, southeast of Oslo, where we burn waste. Burning waste is an incredibly good thing to do instead of putting it in landfill. It's much, much better for the climate. And some of the stuff that's burned here is biogenic, made from wood and textiles and so on. So when that's burned and the CO2 is captured and put underground, that also contributes to taking CO2 from the air and removing it from the climate system. We can also use soil as the carbon storage place. A lot of the agricultural soils in the world contain a lot less carbon today than they did before we started with intensive agriculture. And that's bad for the climate because that carbon is now in the atmosphere. And it's bad for agriculture as well because the soil gets poorer. It's the worst at storing nutrients and storing water and those things. So all the work that's being done at the moment at enriching soils, and for instance, in Norway, a good solution might be to make some charcoal out of biomass and then put the charcoal into the soil that can enrich the soil, and it also is quite a permanent way of storing the carbon in the soils. So that's also something that can be done. And now the oceans are also very important in the global carbon cycle. Here we have the example of a whale. So a whale is a big clump of carbon. It's very big. So what the whale does is, CO2 from the atmosphere gets dissolved in the ocean. And then we have small organisms that do photosynthesis in the ocean. So they take carbon from the water and they use sunlight to build themselves. So they make biomass out of that carbon. And then we have things like this that just go around and eat all that carbon and store it in themselves. And sometimes these whales die where the water is very deep. So then we have what's called a whale fall. It's like a big party for the animals in the deep sea. And when it's very deep, it can take hundreds and even thousands of years for the water down there to come back to the surface. So the CO2, the carbon that's released when this whale is eaten on the bottom, can actually just stay in the bottom for a really long time. And this is called a biological pump. It applies to whales, but also other fish and small animals like plankton. If they fall down and stay on the deep bottom of the ocean, that's also a way to draw carbon from the air into the water and then down to the bottom of the sea. Some people have suggested that if you for instance, just sprinkle some iron on the world's oceans, then that's a way of fertilizing the ocean, because if there was more iron, then you could have more plankton. They kind of grow until they use all the iron and then they stop. If they had more iron, you could get big algae blooms. And then if they all fall to the bottom of the ocean, then you could have a lot more carbon capture and storage this way. You might also get poisonous algae, so it's not so easy to control what you get when you fertilize the ocean. Something that has also been suggested is that you can grow seaweed, like kelp. That's also a great way to capture carbon from the ocean. SINTEF has calculated that if you make a kelp farm offshore, the size of Sogn og Fjordane, it's one of the old fylker in Norway, that would, and then once a year you just put a weight on it and let it sink to the bottom of the ocean. That would be equivalent to all of the onshore CO2 emissions in Norway. Actually, and then I don't know if you think that the size of Sogn og Fjordane in the ocean is big or small, but this is possible, at least. So here's a startup I don't remember if it was the US or Canada, that have been trying to do this and sell some climate credits for growing kelp. So these are ideas that are out there, and I think we will hear more and more about them. But if we don't manage to cut emissions fast enough, and also we don't really manage to pull the carbon out of the air fast enough, we might still want to not get too hot. And then there might be some ways to do that by just reducing the amount of sunlight that hits the surface of the Earth, because that's what's warming us. This picture is from the the little corner between France and Spain, and you see all these stripy clouds. They are not from airplanes; they are made by ships, because these big ocean-going ships they burn some of the dirtiest fuel you have. You have this very nasty exhaust that goes into the air. But what that does, it's all the small particles from the exhaust can act as little seeds for droplets, so they can make clouds. And that's what you see in these tracks. Because the humid air doesn't necessarily turn into clouds, the clouds have to have something to start on. So that means that it's possible to make it more cloudy than it was. People have suggested that we shouldn't have more of these dirty ships, but we could, for instance, spray seawater into the air. If you make really, really, really small droplets, and then the water evaporates, you get tiny, tiny salt crystals. And if they're small enough, they kind of get caught in the updraft over the ocean and get carried up into where they can contribute to creating clouds. So it's been suggested that you could have a fleet of autonomous ships that just cross the oceans and make clouds. But what people are working on in Australia is to do this specifically over the Great Barrier Reef, because heat waves in the ocean are very bad for tropical coral reefs, and we are at the significant danger of losing all of the tropical coral reefs soon because of marine heat waves. So, and marine heat waves they are episodic events. So if there was a way to just cool locally the area, then maybe this could be a way to do it. Sometimes you have very cool periods in the Earth's climate because of very big volcanic eruptions. When you have very big volcanic eruptions that send gases into the stratosphere, then that can create kind of a haze on the sky, and if it takes place near the equator, you can get this hazy sky in the whole world. And periods back in history have been like the summer, the year without summer. There's been famines because the Earth has been cooled a lot from these events. So we know that it's possible to create a lot of cooling with not that much material if you just get it into the stratosphere. And people have suggested that we can do this by You can have planes that are engineered so they can fly in the stratosphere. You can just fire rockets into the stratosphere. You can send up balloons attached to tubes and then have kind of pumps to pump things 10 kilometers into the air. You can try to imagine what that would look like. The kind of nice thing about this is it's possible, probably, or maybe quite cheap compared to everything else that we can do with the climate. And it can be kind of started by some rich guy. The bad thing is that it can be started by some rich guy who thinks he's doing something great, but it's very difficult to know what the result will be before someone has done it for a few years. You can kind of make climate models, but you can't really predict what the effect will be. But there's more and more research also going into this. So MIT has a whole center now working on geoengineering. And yes, yeah, this was a startup. There's a startup working on this, but they just do weather balloons and send them into the air from parks in California. So it's not like they're changing the world yet. But there's also real science going on. Some astrophysicists have decided you can send moon dust into the Lagrange point between the Earth and the Sun. And others suggest that we can have autonomous boats that make ice cubes in the Arctic to have a whiter ocean. This could reduce the Arctic amplification, which is like when you melt too much ice, the water gets darker, and water is darker than ice, so you have more sunlight, and that heats that creates more warming, that melts more ice, that creates more warming, and so on. Maybe we could just freeze the ice back. I think this is maybe one of the worst ideas. But my point is that the more obvious it gets that that emissions have gone too far, the more creative people are going to be about solutions. And I think the line of like what we think is a good and a bad idea is going to be kind of fluid. I think you're going to hear more about these things, and it's always a balance between the good and the bad outcomes. But still, I hope you understand that all of these solutions that are about cleaning up what we did before are bound to be much more difficult and expensive than just not messing it up in the first place. So it means that reducing emissions is really the way to go. So, yeah, I think I'll end there. Thank you very much.
Questions for us? About an hour ago.
Thanks a lot for the wonderful talk. Pretty fascinating solutions for good or bad reasons. But I had a question regarding that. So, what's the math of that? I mean, how much carbon produces for, let's say, a ton of carbon dioxide fixation?
Yeah, that's a very valid question. And I was just at a talk from the answer is because what you need to do, obviously, is you need to account for all of the carbon that goes into making all the materials and all the infrastructure. So that's still unknown, and the numbers I put there are just what's captured. So it's not like the net impact. Very good point.
Any other questions? Any other questions? Oh, back here. Do you want to come closer?
I wonder if any of the solutions are a part of climate mitigation plans, like for European Union, for example, those kind of things at all.
Yeah, so there's when it comes to the negative emissions, they're working on frameworks to account for that at the moment. So For instance, if when CO2 capture is installed at the chemistry, if when they capture like biogenic emissions, then that's not going to be counted because there's no accounting for it yet. But they are making the rules for that at the moment. And in these integrated assessment models that are used as basis for all the climate projections, then at least this bioenergy with carbon capture and storage, where you plant things and then you burn them and you capture the CO2, that's been part of the solution portfolio that uses for quite a while. And I think now also the direct air capture, these machines are also like what you can put into your model and see what's like solution for the future. And that's because there's been like kind of okay numbers for that. Like we know how much it costs to grow plants and burn them and to put CO2 into the ground.
Any other questions? Okay.
Yes, for the existing emissions, is it very costly to have those kind of filter pumps that remove the CO2? Or is that something we want to do that on our scale?
We don't do it on a large scale yet because it's always going to be more costly than not doing it. So our CO2 capture it doesn't give any other benefits to the aluminium plant or the power plant. So if it's very cheap to just release your CO2 into the air, and that's what you're going to do. But now the EU has a quota system for CO2 emissions, and the prices have been going up a lot lately. Just a few years, and even the last months, the prices have been going up significantly. And if they're going to remain at these levels, then it's comparable to what it costs to do this type of mitigation on the plant. But one problem is that even if you put a filter on your pipe, you still need all the infrastructure. So it doesn't help if you just capture the CO2 and there's nowhere to put it. So you have to have trucks that can take it to the port, and then you have to have ships that can transport it, and then you have that's not really in place yet. So there's a lot of things that need to come about kind of at the same time. And the reason why it has been done at all, for instance in Canada, is that you can use the CO2 as a method for getting more oil out of reservoirs. It's very efficient at kind of washing CO2 out from rocks. So then it's been economically feasible to capture CO2 and use that to get more oil.
Yeah, so good answer. Any other questions? No, I have my own question. It's kind of dumb, but still a question. We got emissions. The world gets warmer. With energy. Why are we not harvesting it? Can we harvest it? So instead of it spreading, you get the question? The energy, the extra energy.
The sun?
Yeah.
And why don't we use more solar energy?
No, more like we got more energy because it isn't going on. So isn't there a way to harvest it? Maybe.
Oh yeah, okay, yeah. That's a nice one. So the world is getting warmer because we still get energy in from the sun, but there's more planet-forming gases in the atmosphere, so the energy isn't going out as fast as it used to. Why don't we use that? So in order to make useful work, like to power machines or to get electricity from heat, and the heat, when the sun has hit us, it turns into heat. And what we can get useful work from is when you have a temperature difference. So if you need something that's really hot, and then you need something that's really cold. So like if you have a power plant or something, you get a very high temperature, and then you have to have a river or something to cool it on the other side. But the Earth is not warming that much. It's not really creating a temperature difference we can use. It's just like a tenth of degree. So when it's just like ambient temperature, you can't really do anything with it, unfortunately.
So we found a way to redirect it. Like, could it be possible then?
Yeah, on my roof, when I moved into my house, it has a black roof and it was really hot in the summer. And then I put solar panels on the roof. And now the sun that hits my roof, a lot of it is turned into electricity that I can use to power my computer. And then less of it is turned into heat. So we can redirect it using solar panels. Like before it turns to useless heat, it's in a very powerful form when it hits us from the sun. So we can use it for solar energy. Unfortunately, it's going to still turn into heat in the end, but then we can do that instead of burning oil. It's a very good idea to use solar panels.
Any other questions? No. No. Okay. Then thank you very much. And that's all for this next year from the 13th to the 15th, and I hope to see you all there. So thank you very much for coming. And it's not over. You can just mingle and continue to ask questions and discuss. Oh, of course. And we're important to expand speakers because they are what keeps us engaged. Keep us learning. And thank you all for today.